Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight we are going to continue our discussion on aqueous ionic equilibrium, talking about solubility equilibria. Very fun, very interesting, very exciting stuff. So with that, I present to you Aqueous Ionic Equilibrium Volume 7. As always, your feedback is more than welcome and highly encouraged, so please feel free to, if you're watching this live, drop your questions, comments, thoughts, concerns in the chat. And if you're watching this as a video, please feel free to leave me a comment. Without your feedback, I am totally lost. All right, so throughout this Aqueous Ionic Equilibrium live stream series, we've been talking about buffers and we've been talking about titrations. And one of the things that I mentioned in the beginning of this live stream series is that there's basically three parts to this topic of aqueous ionic equilibrium. We have buffers, which we talked about in the beginning, titrations, which we talked about over the course of the last three streams, and now it is time to talk about solubility equilibria. So what the heck is solubility equilibria and how does it work? Well, I think it would be worthwhile for us to revisit the definition of solubility. So what is solubility exactly? And in layman's terms, solubility is just a measure of how well a substance dissolves in a solvent. Now, we're going to limit our conversation to substances that dissolve in water. So water is going to be our solvent. After all, this is aqueous ionic equilibrium. So we're going to be talking about aqueous solutions in which the solvent is water. So we're talking about how well a substance dissolves in water, right? Or how much of a substance dissolves in a given quantity of water. That is a measure, or that is what solubility is, right? And I'm sure previously in your chemistry education, you learned when you were doing like net ionic equations and precipitation reaction equations and stuff like that, you probably learned how to classify ionic compounds as either soluble or insoluble based on a solubility rules table, right? So you have like all nitrates are soluble, all group 1A metal salts are soluble, all sulfides are insoluble except for this, that, and the other. So you have all the rules, you have all the exceptions, right? But as it turns out, classifying ionic compounds as either soluble or insoluble in this dichotomous sort of way where it's either this or that is a bit of an oversimplification. And we can get a better idea, a more thorough understanding of solubility by considering solubility as more of an equilibrium type of process, right? So if we consider an ionic compound like this one here, this is barium fluoride, BaF2, right? If we consider the dissolution or the breaking apart of barium fluoride into its constituent ions, barium ion and fluoride ion, if we think of that process as more of an equilibrium, that gives us a more accurate picture of what's going on here with solubility. So again, if we represent the dissolution as an equilibrium, well, all equilibria can be described by an equilibrium constant, right? So way back when we were talking about equilibrium, we understood that the equilibrium constant is what shows you the extent of the reaction. In other words, how far the reaction proceeds in either the reactant or the product direction. And the equilibrium constant associated with the solubility of an ionic compound is called the solubility product constant, or KSP. So KSP, solubility product constant, that's the equilibrium expression that represents the dissolution of an ionic compound. And so what I'd like to do is I'd like to go to the whiteboard for a second, and I'd like to see if we can come up with the expression for the solubility product constant, or KSP, associated with this dissolution of barium fluoride, right? So what is KSP equal to, right? Well, again, we're kind of drawing upon our prior knowledge of chemical equilibrium here, but any equilibrium constant is simply going to be the concentrations of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. That's called the law of mass action, right? One of the very first things that we learned when we were talking about chemical equilibrium, right? And so if it's products over reactants, then the expression for the KSP value is going to be as follows, where we have the concentration of the barium ion, right? That's one of the products, times the concentration of the fluoride ion, F minus, and that's going to be squared, right? Because it's the products raised to their coefficients divided by reactants raised to their coefficients, right? And so that's going to be the equilibrium constant expression, the KSP expression, right? Notice that I have omitted barium fluoride from this expression. Why have I left that out? Well, it's because barium fluoride, according to this chemical equation, is a solid, right? Solids do not change in their concentration. The concentration of a solid is determined by the density of that solid. And so since the concentration doesn't change over the course of the dissolution process, it is omitted from the solubility product constant expression. So KSP expressions are very easy because the reactant is always solid and the products are always aqueous. They're ionic, right? They're ions. And so it's just going to be the concentration of the products raised to their stoichiometric coefficients. So you should be able to look at any equilibrium equation associated with the dissolution of an ionic compound and come up with the expression for KSP. It's just going to be products raised to their coefficients. Pretty easy stuff. Now, what do the KSP values look like numerically? Well, let's see if I can find it here. Pulling up a table here of a bunch of ionic compounds and what their KSP values are. And notice that all of these KSP values are very small. 10 to the minus 5, 10 to the minus 19, 10 to the minus 9. They're all very small numbers. And so all of these compounds that are shown here would be compounds that would be considered insoluble according to the solubility rules table, right? But notice that not all insoluble ionic compounds are created equally, right? I mean, you have like barium hydroxide over here with a KSP value of 5 times 10 to the minus 3, right? That would be considered insoluble, but barium hydroxide is looking over here at bismutyl chloride with a KSP value of 1.8 times 10 to the minus 31 and saying, hey, I might be insoluble, but hey, at least I'm not as insoluble as you, right? So again, not all of these compounds are created equally. Some of them, even though none of them dissolve to any significant extent, some of them do dissolve to a greater extent than others, as shown by their various values of KSP across this table here. Okay, so that's what KSP sort of looks like numerically. So we're going to go back to the PowerPoint for a second. We're going to move on. So let's talk about another property of ionic compounds called molar solubility. So molar solubility is just the solubility of an ionic compound, and it's expressed in units of moles per liter. And the molar solubility of an ionic compound can be calculated directly from the value of KSP. So if you know the value of KSP, and you know the balanced chemical equation for the dissolution of the ionic compound, you can easily compute the molar solubility by working out an equilibrium problem similar to the equilibrium problems that we have worked out previously over the course of the last couple of Livestream series. And so what we're going to do is we're going to bang out a problem or a couple of problems in which we calculate molar solubility from the value of KSP. So let's go ahead and get started with that. So I'm going to go over to the whiteboard real quick and let me see if I can paste a problem in here. I might have to rant for a moment. This new version of Microsoft Whiteboard is absolutely terrible. There are things that I used to be able to do with the older version, and I can no longer do them. I used to be able to paste something directly from the PowerPoint into the whiteboard. I can no longer do that. It's just really frustrating. New versions are supposed to be like better and have more features than old versions. This one just sucks. All right, so let me end that rant and actually get the problem up here. So let's see. Do I have the problem? I guess I don't. Okay. All right. So let's say that we are calculating the molar solubility from the KSP value of this chemical equation over here, the dissolution of barium fluoride. So if I refer to my table of KSP values, I'm just going to go look at that off screen for a second and sort of write it over here off to the side. So the KSP, and again, I just found this in a reference table, the KSP for barium fluoride at 25 degrees Celsius is 1.0 times 10 to the minus 6. Okay, so that's sort of given by the problem, so to speak, right? So if I know the KSP and I know the balanced chemical equation here, let me see if I can move that number 6 into the screen. I just realize that I'm kind of running off the page here. And again, I'm trying to acclimate to a new version of Microsoft Whiteboard that is in many ways inferior to the old version that I'm used to. Anyway, so KSP 1.0 times 10 to the minus 6. So how do we work out an equilibrium problem to solve for the molar solubility, the solubility of barium fluoride in moles per liter? So what I'm going to do is I'm going to take this right here. So I'm going to need the space underneath this reaction equation. So I'm going to take this thing over here, see if I can move it. Nope, didn't mean to move the whole thing. Oh my goodness, this version of Whiteboard is not very good. Please bear with me as I work out the kinks. You get something figured out and then they just change it up on you. Still screwing up. Trying to move this thing. Okay, I guess it doesn't matter. I should just delete it. Since I can't move it, I'm just going to delete it. Okay. Thank you for bearing with me, by the way, throughout my technical difficulties. So we have the equation over here, right? And so what we can do is we can, like I said before, we can work out an equilibrium problem, right? And so that involves building an ICE table, I, C, and E. I stands for initial, C stands for change, E stands for equilibrium, right? So in the very beginning, before we throw the barium fluoride into water, initially we have 0 of each of these. 0 barium ion, 0 fluoride ion. Doesn't really matter how much barium fluoride we have because, again, it's not included in the equilibrium constant expression, and so we can ignore it, right? And we know that throughout the course of the dissolution process, some of that barium fluoride is going to dissociate, and so the concentrations of barium and fluoride ion are going to increase by a value that we can assign a variable to. So I'm just going to call it S, S for solubility. So the barium ion is going to increase in concentration by plus S, and the fluoride ion is going to be plus 2S. And the reason why I put that 2 there is because there's a coefficient of 2 in front of the fluoride ion, right? For every unit of barium fluoride that dissociates, 2 units of fluoride ion are going to be generated out of that, right? And so that's why we have this 2S there. And so at equilibrium, right, the barium ion, it's just going to be S, right? 0 plus S is just S. And then the fluoride ion is going to be 2S, right? So we have S and 2S, right? And so we know that the expression for KSP, right? KSP is going to be equal to concentration of barium ion, and that's to the first power, and then times the concentration of the fluoride ion, F minus, squared, right? And so if we take these equilibrium concentrations of barium ion and fluoride ion in terms of S, and we substitute them into this equilibrium constant solubility product constant expression, then we get the following, right? We get S times 2S is equal to the equilibrium constant, which in this case is 1.0 times 10 to the minus 6, right? Now, S times 2S, we can sort of simplify that into 2S squared. So I'm simply going to rewrite this real quick as 2S squared, right? And so now it's just a matter of solving for this S, right? So I'm just going to erase this stuff because we no longer need it. And so we have 2S squared is equal to 1.0 times 10 to the minus 6. So that means that we can divide both sides of this equation by 2. And so that S squared is equal to 1.0 times 10 to the minus 6 divided by 2. So again, I just did that by dividing both sides of this equation by 2. And finally, we're going to take the square root of this. Actually, you know what? I think I made a mistake. Hang on, let me go back. I think I made a mistake. Yes, I made a mistake here. This 2S should have been squared. So I apologize for the mistake. Please forget everything that I just said. So this 2S should be squared because, again, the concentration of fluoride ion is squared. Okay, so that changes our expression quite a bit. So again, I can erase all this stuff. I no longer need it. So it's S times 2S squared. So what we really have is 4S cubed, right? Because S times 2S squared is S times 4S squared, and so that's going to be 4S cubed. So let me rewrite that real quick. So I'm glad I caught that because I would have completely screwed up this problem if I didn't catch that. So it's 4S cubed is equal to 1.0 times 10 to the minus 6. And now we can divide both sides of this equation by 4. And so we get s cubed is equal to 1.0 times 10 to the minus 6 divided by 4. And then finally, to solve for s, we can take the cube root of this expression here, right? So to get s, we're going to take the cubed root of this whole thing, 1.0 times 10 to the minus 6 divided by 4. So this is one of those moments where it's really, really important to know your scientific calculator very, very well, because you need to be able to do not only scientific notation, but also learn how to take the cube root of something. So you really, really want to be familiar with that calculator. So if any of you watching have, if you have your scientific calculators on you and you'd like to follow along with me, I think that would be good, especially considering there's always a chance that I make a mistake in these calculations. So if you'd like to follow along and compute this calculation with me, I would definitely encourage that. So S, which is the molar solubility, is equal to this thing. So let me type that into my calculator real quick. So we have the cubed root of 1.0 times 10 to the minus 6 divided by 4. Make sure I have my parentheses right. And I got a value of 6.3 times 10 to the minus 3. 6.3 times 10 to the minus 3. That is the molar solubility of barium fluoride. So all we did here was just worked out an equilibrium problem. We set up our ice table, right? And then that gave us these concentrations of our ions in terms of S. And then we substituted those concentrations into the solubility product constant expression and then solved for S. And that gives us this value right here, 6.3 times 10 to the minus 3. So I hope that was useful for you. By the way, if you find this content valuable, I would highly appreciate your support in the form of leaving a like on this video. It goes a long way to help with discoverability. And also, if you are feeling generous, you can leave a super chat or even donate via Streamlabs. I am now accepting Streamlabs donations. If you go to streamlabs.com/benschemvideos, there's a link in the description. You can tip me. I think you could do text-to-speech donations, although I'm not really very tech savvy, so I'm not sure if that works or not. I don't know how well that works, but just letting you know that it is there. And so we're going to move on and do the next problem real quick. So let me just sort of import the image of the problem, which I didn't used to have to do, but I have to do now because this god-awful update to Microsoft Whiteboard. It's terrible. Okay, so we're going to do this problem right here. Let's see if I can open it up. Yeah, looks like I got it. Okay. So, all right, so this problem, we're actually going to go in the opposite direction to what we did before, right? So instead of going from KSP to molar solubility, we're going to be given molar solubility and calculate the KSP from that, right? And so this problem says that the molar solubility of silver bromide in water is 7.3 times 10 to the minus 7 molar, and we are asked to find KSP. Now, the first thing that I always like to do when it comes to problems like these is to simply write out the chemical equation associated with the problem, right? The chemical equation associated with the dissolution of silver bromide, right? So if we have silver bromide, that's AgBr, and that is a solid, and that's going to react reversibly to form the silver ion and the bromide ion. The silver ion is Ag+, and that's aqueous. And then the bromide ion, that is Br-, and that is also aqueous, right? So let me see. I'm going to try to resize this a little bit. Let's see if I can. Yeah, looks like I can do that pretty easily. Yep, that looks pretty good. Okay, so again, we're going to work out an equilibrium problem similar to the one that we worked out in the last problem, right? So we're going to have our ice table. So we're going to have I for initial, C for change, E for equilibrium. Of course, initially, we don't have any silver ion. We don't have any bromide ion. The change, again, they're going to increase by plus S. It's going to be plus S. Notice there's no 2 or 3 in front of the S because both of these silver and bromide ions have an understood coefficient of 1 in front of them. And of course, at equilibrium, we are going to have S for both. Both of the concentrations of silver and bromide ion are going to be S. And so if we now sort of plug this into the expression for the solubility product constant, let's see if I can do this in another color. I'll just go back to blue. That's another thing, is this whiteboard, like they used to have more options for the like pen colors and stuff like that, and now I'm it's just not good. Like this update to this software sucks in every way imaginable. I know I can't shut up about it, but it's really, really bothering me. Okay, so the KSP, as we know, the expression for that, as it is with any equilibrium constant, it's going to be concentration of products, that's Ag plus, and the concentration of Br minus, right? So that's the expression for the solubility product constant. Both of them at equilibrium are S, and so it's going to be S times S, right? S times S, and we can simply rewrite that as S squared. So S squared, that is equal to the solubility product constant. So we have the molar solubility, we have the molar solubility, right? S, that's given. And so really all we have to do is square it, right, to get the KSP value. And so that's simply going to be 7.3 times 10 to the minus 7. This whole thing is going to be squared. And that'll get us KSP. It looks like I've run out of room, so let me, if I can shrink this down just a little bit more, give myself some room here. 7.3 times 10 to the minus 7 squared. So again, if you brought your scientific calculator with you, you can follow along with me while I bang out this calculation real quick. 7.3 times 10 to the minus 7, and that is squared. Got a message in the chat from Kitty. It says, hey, Ben, couldn't make it last week, but I'm also quite busy this week because it's my birthday this upcoming week. Happy birthday! I hope you and your fam are doing great. Yes, we are. Thank you very much for stopping by and saying hello. So 7.3 times 10 to the minus 7 squared, that gives us a KSP value for silver bromide of, let me do this in green. This is going to be, what did I get? 5.3 times 10 to the minus 13. Very, very small number. 5.3 times 10 to the minus 13. So again, it's basically the same problem as before. Although instead of going from KSP to molar solubility, we went from molar solubility to KSP, right? So it's the same process. It's just, different known, different unknown, but you use the same relationship, the same algebraic equation to solve for your unknown, right? So that's the solubility product constant and molar solubility. So let us delete all of that, and we're going to go on a little journey back to the PowerPoint as we continue forward in this discussion on solubility equilibrium. So, all right. So let's say we want to compare the solubility of a couple of ionic compounds. What could we use? In other words, what could we compare? What properties could we compare to accurately assess the comparison of the solubility of two ionic compounds? Well, here we have two ionic compounds. We have copper 1 chloride and we have barium fluoride, the one that we were looking at a few moments ago. And their values of KSP are shown and their molar solubilities are also shown, right? And so for copper 1 chloride, it's 1.2 times 10 to the minus 6. That's the KSP value. For barium fluoride, it's 1.0 times 10 to the minus 6. And so you might say, okay, well, copper 1 chloride has a larger KSP value than barium fluoride, and so that must mean that copper 1 chloride is more soluble. It has a higher solubility, but that is actually false. It does not. If you look at the molar solubilities, the molar solubility of copper 1 chloride is 1.1 times 10 to the minus 3, and barium fluoride is 6.3 times 10 to the minus 3. So even though the KSP value of copper 1 chloride is larger than the KSP value of barium fluoride, the molar solubility of copper 1 chloride is smaller than the molar solubility of barium fluoride. So how could that be the case? Well, the answer is that the molar solubility depends not only on the KSP value, but also the stoichiometry of the dissolution. So if we look at the equations associated with the dissolution of these compounds, copper 1 chloride and barium fluoride, we can see here that there's a pretty big difference between these two processes, right? In the case of copper 1 chloride, right, it dissociates into two ions, one copper ion and one chloride ion. But in the case of barium fluoride, however, we have three ions in the products. We have one barium ion and we have two fluoride ions, right? So it depends not only, molar solubility depends not only on the value of the solubility product constant, but it also depends on the stoichiometry of the dissolution. How many ions are generated by the dissolution of that ionic compound, right? And so if we are comparing, let's say we're comparing these two ionic compounds here, right? This is copper 2 hydroxide, and this is barium fluoride once again. And so the question is, could we compare the KSP values of these two and get an accurate assessment of which one has the higher solubility? And the answer is yes, we can. And the reason why is because these two ionic compounds have the same dissociation stoichiometry. They produce the same number of ions in aqueous solution during the dissolution process. So you can compare the KSPs of these two and conclude that barium fluoride with a much, much larger value of KSP is more soluble than copper 2 hydroxide, right? 1.0 times 10 to the minus 6, much, much larger number than 2.2 times 10 to the minus 20, right? And so if we look at the chemical equations for these two, and I'm going to try to put myself over here so I'm not in the way. So if we're looking at the equations for these two, we can see that both of these ionic compounds produce the same number of ions, which is 3 in solution, right, when they dissolve. Right? 3 ions in the case of copper 2 hydroxide, 3 ions in the case of barium fluoride. They have the same dissolution stoichiometry, right? Right. So again, what I'm trying to say is that the value of KSP can only be used to compare relative solubilities between ionic compounds if the dissociation stoichiometry of those ionic compounds is the same. If not, you cannot use KSP to compare the solubility. So hopefully that makes some sense because we are moving right along. So now we're going to talk about something that we've talked about before. We've talked about this before. It's called the common ion effect. So the common ion effect. Hopefully we remember it, but even if you don't, I think I'll explain it well enough and from the beginning, like bottom-up approach, so that you understand it, even if you don't know what it is and this is your first time seeing it. So imagine two scenarios. Imagine one scenario in which we put some barium fluoride in water, right? Pure water. We're putting some barium fluoride in water. And imagine another scenario in which we're putting barium fluoride into a solution that already has some fluoride in it. Let's say that solution is 0.1 molar sodium fluoride, right? So we're putting barium fluoride into a solution containing sodium fluoride, right? So sodium fluoride and barium fluoride, they have an ion in common. That's why they call it the common ion effect. And the ion that these two compounds have in common is the fluoride ion. And so my question is this, excuse me, my question is the following. Do you think that barium fluoride is going to be more soluble or less soluble when you put it in 0.1 molar sodium fluoride than it is when you put it in pure water? Let me repeat that. Does the solubility of barium fluoride increase or decrease relative to pure water when you put it in an aqueous solution already containing sodium fluoride? That is the question. Let me know what your thoughts on this are. I mean, even if you guess, you have a 50-50 shot of getting it right. So that's the question. And the answer is that the solubility of barium fluoride is actually going to be lower when you put it in a solution already containing some fluoride in it than when you are just putting it in pure water. And to demonstrate this, I'm going to take you back, excuse me, I'm going to take you back to the whiteboard here, and we're going to pull that barium fluoride equation back up again. So bear with me while I find it here. So this is barium fluoride. Did I get it? Looks like I did. Okay, let me resize it here. Right? I think this is probably, maybe down here is a good place to put it. Okay, so Kitty says, never mind, I was wrong. Hey, doesn't matter. At least you participated. At least you tried. And that really is all I ask. Finding the answers is just as important as knowing them, right? So, okay, so imagine that we're dissolving this barium fluoride in water, or we're dissolving as much of it as we can, right? This is a compound that would be considered insoluble according to the solubility rules. So even if it does dissolve, it's only going to dissolve to a very, very small extent in the first place, right? And if we already have some fluoride ions, right? I'm just going to highlight this fluoride here because that's what we already have in the solution, right? So what does adding a product do to a chemical reaction that is at equilibrium? That's the question. What does having additional product do to the reaction at equilibrium? And to understand this, we must understand a concept called Le Chatelier's principle. Let me see if I can write that. I can't remember exactly how to spell it, but it's Le Chatelier's principle. I think it's worthwhile to write this, right? Le Chatelier's principle. And what Le Chatelier's principle basically says is that for a reaction at equilibrium, if that reaction is disturbed, then the reaction will respond in a way that opposes the disturbance in order to achieve equilibrium once again, right? And so by adding more of this fluoride ion relative to pure water, that equilibrium is going to shift in the left direction, right? If you disturb that equilibrium by adding a product, then the reverse reaction is going to speed up, consuming more of that product to try to reach equilibrium once again, right? And so that's why the solubility of barium fluoride is going to be lower in a solution that already has some fluoride ion in it than if it was just placed into pure water. It's according to Le Chatelier's principle. So this is the effect of a common ion on solubility. And we can understand this better by going through the motions and working out an equilibrium problem like we did before. So let me erase all this stuff and just sort of bring this back up here. Let's see if I can use my mouse instead of the pen to bring this back up. Okay, so again, so we can do the same thing as we did before, working out an equilibrium problem. So we're going to have our ice table, right? So that's why. Okay, so we're going to have initial change equilibrium, right? And we're going to have, in the case of our barium ion, we don't have any of that in the beginning, but if our fluoride ion, we already have some of that at the beginning. What did we say? I think we said 0.1 molar, right, was the initial concentration of fluoride, right? As the barium fluoride dissolves, there's going to be some barium ion that's generated. We'll call that plus S. That's the change for the barium ion. In the case of the fluoride ion, that's going to be plus 2s, because there's a coefficient of 2 in front of that fluoride ion. For every 1 unit of barium fluoride that associates, 2 units of fluoride ion are generated, so that's why we put that 2 there. And so at equilibrium, for barium ion, it's going to be simply S, and for the fluoride ion, it's going to be 0.1 plus 2s, right? Now, if we plug those into the expression for KSP, right, so KSP is equal to concentration of barium ion, Ba2 plus, times the concentration of fluoride ion, and that is squared, right? So if we take these two values, right, we're going to substitute those in. So barium ion, that is simply S, and for the fluoride ion, that's 0.1 plus 2s, and we're going to square that, is equal to the value of KSP. And earlier, I think we were doing this problem, we said that the value of KSP, according to our table of KSPs, is 1.0 times 10 to the minus 6. I just realized I'm kind of running off the page, so I'm going to sort of drag this over, give myself some more room. 1.0 times 10 to the minus 6 is equal to all of this here. So this is looks like it's a pretty complicated equation, but we can apply the x is small approximation to this problem to make the equation much more easy to solve. So again, the x is small approximation, or in this case, the s is small approximation. What we're basically saying is that this value of s is very, very small, and so 2 times the value of s is also very, very small compared to the number that we're adding it to. So we're adding it to 0.1. I think that this value of s is very, very small compared to 0.1, and so therefore I'm just going to omit it from this equation here because it's so small, right? It's like stepping onto a scale with a penny in your pocket, right? The reading on that scale is probably not going to be different whether you have a penny in your pocket or not, right? That's the logic behind omitting this from the equation here, right? And so this becomes a lot easier to solve. S times 0.01 squared is equal to 1.0 times 10 to the minus 6. 0.1 squared, that's going to be 0.01. So 0.01 s is equal to 1.0 times 10 to the minus 6. And so we get s is equal to 1.0 times 10 to the minus 6 divided by 0.01. So the molar solubility is going to be 1.0 times 10 to the minus 6 divided by 0.01. So bear with me while I plug that into my calculator. Again, if you're watching and you'd like to follow along, I would highly recommend that. In fact, I think that's the best way to get the most out of these videos and these streams is to follow along with your calculator and we do these problems together. All right, so 1.0 times 10 to the minus 6 divided by 0.01. That is a value of 1.0 times 10 to the minus 4. 1.0 times 10 to the minus 4, right? And so notice that this value of 1.0 times 10 to the minus 4, right? The molar solubility of the barium fluoride when we put it in a solution that already has 0.1 molar fluoride ion in it, right? This is less than the molar solubility of barium fluoride when there was not initially any fluoride ion in the solution, right? I think, well, what did we say? It was 6.3 times 10 to the minus 3. I think that was the molar solubility that we calculated in the absence of any existing fluoride ion before we drop the barium fluoride in, right? So mathematically, it also makes sense when we work it out like this. And again, all this stems from Le Chatelier's principle, right? By having that product in there at the beginning, you're adding more of a product. That's a disturbance to the equilibrium. The equilibrium, according to Le Chatelier's principle, is going to react in a way that opposes the disturbance. So the reverse reaction where products become reactants is going to speed up to achieve equilibrium once again. That's the common ion effect when we apply it to the solubility equilibrium, right? So let's go back to the PowerPoint and move on here. We have just a couple of things to talk about before we wrap things up. So let's go back. So we talked about the common ion effect. Now let's talk about the effect of pH. The effect of pH on solubility. So remember, pH, of course, that's just a measure of acidity or alkalinity, right? Low pH means high hydronium concentration, low hydroxide concentration. High pH means high hydroxide concentration, low hydronium concentration. And so the question is, what effect, if any, do you think pH of an aqueous solution has on the solubility of an ionic compound in water? Let me repeat that. What effect, if any, do you think the pH of an aqueous solution has on the solubility of an ionic compound that you put into that aqueous solution? Interesting question. It kind of requires some thought to reason your way through this one. And so I'm not surprised that I don't see any answers in the chat right now. But in order to sort of demonstrate this concept, I want to bring your attention to a particular, the dissolution of a particular ionic compound. And I'm going to go into the whiteboard to show you guys this. So bear with me. I just have to upload an image here. Because again, I used to be able to copy and paste things from PowerPoint into the whiteboard, but according to the brilliant people at Microsoft, I should no longer be able to do that. So let's see. Where is it? Okay. I think I found it. Okay. Okay. I'm going to try to enlarge it and get rid of that. Okay. I think we are all set here. Just going to make this more sort of in the middle here. Okay, so this equation describes the dissolution of copper 2 hydroxide into its constituent ions, where we have 1 copper ion and 2 hydroxide ions. And so the question is, what effect would the pH of this aqueous solution have on the solubility of this copper 2 hydroxide, right? Good question. Well, let's think about what pH actually is, right? So if the pH is high, right? If we have a high pH, right? If we have a high pH, what does that mean in terms of our hydronium and hydroxide concentrations? That means that our hydronium concentration, H3O plus, is very low. I'll just indicate that by using this downward arrow here. And our hydroxide concentration, our OH minus concentration, is high. That's what a high pH means. It means that your hydroxide concentration is high and your hydronium ion concentration is low. Now, if you have a low pH, then it's the opposite, right? Concentration of hydronium is high, and the concentration of hydroxide is low, right? Now imagine the scenario in which we have a high pH, right? A high pH, right? That means we have a solution that has a large concentration of hydroxide ion. Now, if we have a large concentration of hydroxide ion, that's a product in this equation, isn't it? And if we add a product to a reaction at equilibrium, well, that's a disturbance. And according to the Le Chatelier's principle, this reaction at equilibrium is going to respond in a way that opposes the disturbance. And so it's going to react more in the reverse direction to become the reactant, right? The copper 2 hydroxide. And so in other words, what I'm trying to say here is that at a high pH, copper 2 hydroxide is going to be less soluble than it would be in an acidic or a neutral solution. Again, because by having that high pH, you're adding more product. You're disturbing this equilibrium, causing it to shift in the leftward direction. So this equilibrium is going to shift left, and you'll have a lesser solubility as a result of that, right? Now, if you have a low pH, right? If you have a low pH, well, what's going to happen there? Well, that means you're going to have a lot of hydronium ion in there, right? And that hydronium ion is going to react with the hydroxide ions that are produced by the dissociation of this copper 2 hydroxide, right? And if you're adding more hydronium ion, it's going to react with that hydroxide, right? And so it's going to be taking away a product, right? Taking away a product from a reaction at equilibrium is a disturbance. And the equilibrium reaction is going to act in a way, according to Le Chatelier's principle, to oppose that disturbance. And so it's going to generate more product to replace the product that's missing after having reacted with the hydronium ion caused by that low pH, right? So at high pHs, this stuff becomes less soluble. At low pHs, greater acidity, this stuff becomes more soluble, right? And so that's the effect that pH has on solubility, but it only applies when your anion is basic, right? It only applies when your anion is basic. Now, it could be strongly basic, it could be weakly basic, but only when your anion is basic does the pH have this effect on solubility, where low pH, greater acidity, yields a higher solubility. If your anion is not basic, then the pH won't have any effect on the solubility. And so with that, I'm going to take you to the last slide of this presentation. So we're going to go back to the PowerPoint. Actually, I think I can stay on the whiteboard. I don't know why I did that. Let me go back to the whiteboard real quick, and I can sort of delete all of this, and I'm going to paste in another problem here. So this is the problem here. Okay. I'm going to hide that, enlarge that. Okay. So this question asks us to, it's actually not a question. I don't know why I put a question mark in there, but please disregard that error. So it says to determine whether NaCl, sodium chloride, this stuff right here, that's potassium acetate, and lithium hydroxide, LiOH, would be more soluble in acidic solution, right? Would these compounds be more soluble in acidic solution? And again, we kind of answered this question earlier, right? We said, well, if your anion is basic, then yes. If your anion is not basic, then no, it's not going to be more soluble in acidic solution. So let's start by turning our attention to NaCl, right? And again, the first thing I always like to do with problems like these is to write out the equation for the dissolution, right? So for NaCl, that's NaCl, and that's a solid, is going to react to form the sodium ion, Na+, aqueous, and the chloride ion, that's Cl-, aqueous, right? And so if we look at our anion here, that's the chloride ion. So we need to figure out whether this chloride ion is basic. Is it basic or is it pH neutral? So this is kind of digging back to a concept that we learned in the last live stream series about acids and bases, where we learned about the acid-base properties of ions and salts, right? And anions can, but not always do, act as bases, right? If your anion is the conjugate base of a weak acid, then that anion itself is going to behave as a weak base. But if your anion is the conjugate base of a strong acid, then it is pH neutral. So the conjugate acid of HCl, right, Cl- is the conjugate base of which acid? That would be HCl, right? And HCl, as we all very well know by now, at least we should, is a strong acid. So Cl-, right? That's the conjugate base of a strong acid, therefore Cl- is pH neutral. And so since Cl- is not acting like a base, the pH will not have an effect on solubility, and so sodium chloride is not going to be more soluble in an acidic solution. Let's go ahead and move on to the next example. Let's move on to potassium acetate. So again, I'd like to write out the equation for the dissolution of potassium acetate. So what we're going to get is the following, where we have, let me close that. I don't know how to get out of that. Okay, so we have potassium acetate, that's K, and that's C2H3O2, right? And that's a solid. That's going to react to form the potassium ion and the acetate ion. So the potassium, that's K+, aqueous, and then the acetate ion, that is C2H3O2-, and that's aqueous. And so in this case, our anion is the acetate ion. And so the question is this anion basic? Does this anion, this acetate ion, behave as a base, right? And so really the question is the acetate ion the conjugate base of a strong acid or a weak acid? If it's the conjugate base of a strong acid, then it's pH neutral. If it's the conjugate base of a weak acid, then it is a weak base. Acetic acid, right? It's the acid for which the acetate ion is the conjugate base. Acetic acid is a weak acid, as we should know by now. Again, we've had enough practice with a lot of these strong and weak acids. We should be at the point right now in our chemistry education where we can look at the formula for a common strong acid or weak acid and immediately tell that it's a strong or a weak acid, right? Like immediately, as soon as I looked at that acetate ion, I'm like, oh yeah, that's the conjugate base of a weak acid because I've done so many problems like this before. That's what I want you to be able to do, right? So again, since the acetate ion is the conjugate base of a weak acid, acetic acid, the acetate ion behaves as a weak base. And since this behaves as a base, it is going to depend on pH. The solubility of potassium acetate is going to depend on pH, and it will be more soluble in acidic solution. So for the sodium chloride, it was no, and for potassium acetate, it's yes, right? So let me, whoops, didn't mean to do all that. Let me erase everything here and just go back to, there we go. All right, so the last one that we're going to do is lithium hydroxide, LiOH. As always, what I like to do first is just write out the equation for the dissolution. So we have LiOH, lithium hydroxide, that is a solid, and that is going to react or dissociate to form the lithium ion, Li+, aqueous, and that's also going to form the hydroxide ion, that's OH-, aqueous, right? So that's our equation. Our anion is the hydroxide ion, right? So the question is, does the hydroxide ion behave as a base? Yeah, it does. Like hydroxide is the definition of base, right? It's the definition of like the higher your hydroxide concentration is, the more basic your solution is. So since our anion is definitely behaving as a base, a very strong base, the strongest base that you can have in water, in fact, the hydroxide ion, yes, this is going to be dependent on pH. The solubility of lithium hydroxide will be higher when you have an acidic solution where you have a lot of hydronium and not much hydroxide. And it's not going to be independent of pH as the sodium chloride was. So that was just an example of how sometimes, depending on the anion of your ionic compound, sometimes you have a situation in which the pH does indeed have an effect on solubility, but not always. All right, everyone. So I think that is going to do it for tonight. Thank you very, very much for watching. I thoroughly enjoyed presenting this information to you, and I hope you got something valuable out of it. And I would also hope that if you didn't get something valuable out of it, then you would tell me. I have a thick skin. I can handle the most brutal criticism ever. So that came off kind of awkward. But anyway, all right, thank you guys for watching. If you enjoyed the stream, I stream Sunday nights, 9 o'clock p.m. Eastern. I sincerely hope to see you in the next stream, and I will talk to you later. Take care.